Here's another problem for review solution, part 2 review problem 41, down the drain. The goal is to take some data about diameter of plug versus drain time, make that clearer, and this is diameter plug in inches versus drain time in minutes, and to create a model of this thing. Okay, so first thing I did was I created a scatter plot. I think we all know how to do that on the TI. And so what we see is a pattern that's going down and then bending and sort of avoiding zero. Okay, so what I tend to do here is I tend to think about what kind of functions that have this shape. Well, anything that is really high and then goes down low near zero, that reminds me of 1 over x. Okay, so let me go ahead and plot that. And if you want to, you can use the calculator to plot that. We're not doing the actual expression yet. We're just playing around here. Okay, well, we don't need negative values, but for positive values, that does have this kind of shape. Okay, so if y, let's change this to approximately equals. Okay, this might be y is very roughly approximately equals 1 over x, or maybe 100 over x, or 50 over x, or something like that, but very roughly this kind of shape. Well, then we want to get it where y is as closely related to x as possible. So the new y, okay, the new y is going, if we define that to be 1 over y, well then that's going to approximately equal x. Okay, let's see. Well, so I can do that here. I'm just going to call this, let's say, new y. Okay, and the way I do it here is I add a formula, and I'm just going to say 1 over the drain time. Okay, let's see if it works. Boom. Well, okay, it's going uphill. Now the book often says you want to preserve the sense of the association. It's still going down, so they would have used a minus. I'm not that huge a fan of that, to be honest. But I don't know. It still looks curved to me. And if we did a least squares line and then look at the residual plot, oh yeah, that's definitely curved. Okay, and the residuals aren't even that small either. Okay, well, I guess these are in thousandths, so they're not super big, but there's definitely seems to be some sort of curvature here. I think we can do better. Okay, so let's try something else. I'm gonna edit that formula, but first let's go back to here. What other functions have this general shape but are maybe more curved upward or less curved upward? Well, we could try 1 over x squared. Okay, so let me actually plot that in here. Let me come out all the way here. Let me plot them together to sort of show you 1 over x squared. Okay. Let me make sure it's clear which one is which. Let's say this is a thick one. So this will be the new one. Oh wait, the old one will be thick and the new one will be thin. Okay, so here's 1 over x, and here's 1 over x squared. Starts out steeper and gets flatter. It's kind of more aggressively bending. It was steeper here and flatter here. And let's see. So that's more aggressively bending than the other one. How does that correspond here? Well, we tried to take some of the bend out of this with a re-expression, and we didn't do enough. So that suggests we actually kind of need to have something like, let me bring this back, something like this model. Okay, so what would that be? Well, if we want to cancel out a 1 over x squared, then maybe we can do this. Okay, if I take something that looks like 1 over x squared and I square root it, that'll kill the square, and I take the reciprocal, that'll kill the 1 over, that'll now be maybe close to x. Well, let's try it. Okay, and I don't know why that's so small. Okay, actually, there we go. Okay, so let's try that as our new y. Now again, if that seems a little hard to parse for you, like, wait, how would you know x squared, root y, whatever? Just try the two possibilities. Kind of the two possibilities that are near here are, you could take this and you could take the square root of it, or you could take this and you could square it. And one of them should look significantly better than the other. Okay, so if I tried 1 over drain time squared, believe me, it would get worse. I'm not sure if I'm going to take the time to do that. Okay, now remember, if you're doing this on the TI, let me just delete this now. If you're doing this on the TI, you're going to do things like go to L3 at the top of the stat edit menu, and it's going to have a little when you do that at the bottom, it's going to say L3 equals. And then you would just do 1 over, press the square root button, and then like L2. Okay? And then that's going to create your L3. Okay? And then you're going to can do a stat plot, like a scatter plot of L1 and L3, L3 versus L1. And you can also do a linreg. That's the A plus BX. That's the stat calc 8. And you can do L1, L3, and remember to do Y1 so you can plot it. Okay, so this is what we get here. I think I need to rescale graph axes. Okay, so this definitely looks better. Okay, these are right on the money. We've just got one that seems a little off, and that maybe is a little high. Okay, these residuals are definitely smaller, and it's hard to see how we could get better because these are a little on the high, then suddenly that's low, and then that's high again. There's not this clear pattern of just one arc, either down, up, or up, down, up. Okay, and so it's very unlikely with a simple model we're going to get better. There's also something to think about. The book tends not to emphasize this, but you maybe want to think a little bit about actually like physics and things like that. What's this diameter square? We're basically saying that if 1 over root y is linearly related to x, again, we're saying that y, the drain time, is related to 1 over x squared. Well, what does diameter squared look like? Oh, diameter squared, hey, if you multiply that by pi, okay, well, divided by 4, actually, because it's pi r squared, that's the area of the drain hole. It makes a heck of a lot of sense that the area of the drain hole, when that gets bigger, that's the denominator here, the drain time should get smaller, okay? So the claim is the very unobjectionable claim, which is the drain time is inversely proportional to the area of the drain hole. Okay, that's not too surprising, and the data definitely seems to bear that out. It's not perfect, of course, because there's all kinds of other little factors and errors and things like that, but it looks pretty good. Okay, so we've created our model, we've done our re-expression, we've checked our residuals. The R value, notice, is so close that Fathom can't even tell. I don't know if you can read this too well. It's 1.00 is what it's getting. And the model is that our re-expressed y, and we should put a hat on it because this is just a prediction now, okay, is equal to 0.219 times diameter plus 0.0024. And then we can use that to our heart's content, plug in any diameter you want, and get this. So for example, if the diameter was equal to some value that's not on this list, let's say a diameter of 1.75, then we would plug it in here. And let's evaluate that. Let's pick that up and just put it where it belongs. Okay. And drop that. Okay. And then you just solve for y, or y hat. Okay. So square root of y hat, I'm just going to take 1 over both sides. 1 over 0.38565. Calculate that. So that's equal to 2.593. And then square both sides to get y hat. Oh, I just wanted y hat. Thanks. Equals 2.593 squared. And I'll let it calculate that. 6 point something, yeah. 6.724. Probably don't need that much accuracy. Okay. So the claim is that a 1 3/4 inch diameter drain hole would be, surprise, surprise, between 5 and 10 minutes of drain time. That's a good reality check. This should come out between 5 and 10. And about 6 3/4 minutes of drain time. That's not saying it's perfect. That's not saying it's really what y is going to be. But we have a pretty good amount of faith in this prediction. Now, if you ask me to predict a 5-inch diameter drain hole, that I might be more wary about because that would be extrapolation. 2.25, 2.5, even 3, maybe I'd be happy with that because this model seems so good and because we have a physical reason to think that it should be close. But there might be other factors that come in when you go outside of this region. So extrapolation is always dangerous.